Hi guys, in today's video we're going to take a look at the work energy theorem. So we're going to see that this gives us a different approach to similar problems that we've solved before using Newtonian mechanics, but now we'll use energy considerations instead. So we're going to take a totally different approach and we'll get the same answer we would have gotten with Newtonian mechanics. So especially in the energy conservation videos, you'll see how this can save us a lot of time. In today's video you won't necessarily see that time being saved, but we're going to get a good understanding of how to apply these work energy theorem, how to apply energy considerations to solve these types of problems. So this will be very important, so make sure you understand the building blocks, and then we'll sort of put it to its full utility in a couple videos. So for today, we want to remind ourselves what is the work energy theorem. So it basically tells us that the total work being done on an object is going to equal the change in kinetic energy. So I'm going to write this delta means change. I'm going to write this again as kinetic energy final minus kinetic energy initial. So that's just what the change is. So the one thing we see about this work is that it is either positive, negative, or zero. So we'll assume that we have non-zero work being done for this section. And so the idea is it's a number. It's not a vector, right? This is a scalar. So that means that the work is either positive or negative, and we can see if there is some work, we can see that it will be positive if it works to speed up the object, and it will be negative if it works to slow it down, right? If the work is positive, the kinetic energy final must be greater than the kinetic energy initial. Therefore, we must have sped up our object, and vice versa. So this is our sort of work energy theorem here in one line. And then the other thing we need to note is the form of work. And so the form of our work is just going to be force dotted with a displacement vector. So this S is displacement vector. So let's look at a simple scenario to understand what's going on here. So we can think of a block, and maybe we push it with some force to the right. So we'll assume it starts at rest. As soon as we push it, it's going to move to the right. So this displacement vector is defined as a vector which points along the direction of our motion, and the size of this vector is just going to be the distance that the box has traveled. So in this case, we see we'll do some work. Our work is going to speed up our object from rest to some positive velocity. So it's going to work to speed up our object. We'll have a positive work done, and that will just be equal to F dot S. And since F and S are in the same direction, that is just the magnitude of F times the magnitude of S. So in the next video, we're going to look at how to deal with this dot product when these arrows are not pointing in the same direction. But in this case, we're just going to look when the force vector is along or against the displacement vector. Okay, so let's look at the problem statement for today, and that reads as follows. Consider the system below. The rope and pulley have negligible mass, and the pulley is frictionless. The coefficient of kinetic friction between the 8 kilogram block and the tabletop is mu k is equal to 0.25. The blocks are released from rest. Use energy methods to calculate the speed of the 6 kilogram block after it has descended 1.5 meters. At this point, you should pause the video, reread this problem a couple times, and maybe even try it on your own. Okay, so now that we've read out the problem, let's look at the scenario which we've drawn over here. So we see whenever we release these blocks, they're going to accelerate sort of in this fashion, meaning that block B will accelerate downwards. That's going to pull block A to the right. And so I've just drawn out these displacement vectors, which just point along the motion. And we're also told that block B should fall a distance of 1.5 meters, and then we want the velocity at that distance. So the size of this displacement vector will just be 1.5 meters. So our first step will be to draw out the free body diagrams here. So for block A, that will amount to drawing out the forces. So we see we have our force of tension pulling to the right. Of course, we have a normal force acting up from the surface and a gravitational force on block A. And then similarly, we have a frictional force because we're told this is a rough surface. So we've done this a bunch of times, but this is our free body diagram for block A. And then for block B, we sort of have more of the same, which is to say we have a gravitational force on B pulling downwards and a tension force pulling up. So note that these two tension forces are the same because this rope is massless. So what we want to do now is draw on these displacement vectors because we're going to want to use energy considerations. So our work is going to be important. And so for this, we know block A should move to the right, so it's going to be to the right. Block B should move down. We're really just drawing these two vectors on our free body diagrams. So now we want to use the work energy theorem to see if we can get somewhere in order to find the velocity. So we know the work energy theorem relates work to a kinetic energy, which has to do with velocity. So it's a good idea that this might help us out. So if we look, we're going to apply the work energy theorem to block A first and then to block B. So for block A, our work energy theorem tells us the total work done should be equal to delta kinetic energy. And so in this case for block A, the change in kinetic energy will of course be the kinetic energy final minus the kinetic energy initial. But since these blocks both are released from rest, the initial kinetic energy is just going to be equal to 0. So that means work total should really be equal to final kinetic energy, which is 1/2 ma v squared. We'll call this v final because that will be what we'll solve for. So we want to solve for v final. So we're in a good position. We already have v final in our equation. And now we just need to figure out what the total work done is. So the first thing to note here, and this is very important, is that the normal force and the gravitational force should not do any work on object A, on block A. And the reason for that is, we can see it one of two ways, is that our force is always, this is our work. Let me erase this. Our work should be equal to our force, which is a vector, dotted with our displacement vector. So this is the form of each work. It's just going to be force dot with displacement. So in this case, we see that the gravitational force and the normal force are both perpendicular to the displacement vector. And so if you remember dot products, the dot product of two perpendicular vectors is always 0. So that's one way to see it. Another way to think about it is we know the work should be the change in kinetic energy. And so these two forces should not be working to speed up or slow down the block. They're just going to sort of be pulling in the vertical direction. There's no motion in this vertical direction, so those should not be doing any work on the object. So the work total is going to come entirely from these two forces, the tension and the kinetic friction. And so that's to say work total will really be work tension plus work of kinetic friction. And so this is our total work, and we also know, of course, this is still equal to 1/2 ma v final squared. So this is our equation. Maybe I'll put an arrow. This is now our equation. It's just whatever the work by tension plus the work by friction should be equal to 1/2 mv squared. And so now we just remember again the form of our work. So one thing we see is that our tension force points along our displacement vector, so that should be a positive work. This should do work to speed up the object. And so that's going to have the form of the tension force. So this is really the magnitude of the tension force times the magnitude of the displacement vector. So again, this is the distance traveled. So our work is tension times the displacement. And then in this case, we're going to subtract off our work done by friction because we know this is negative, right? So we're going to add our negative work by friction. And the reason it's negative is it points in the opposite direction as our displacement. So the work done by friction then will just be negative force kinetic friction times displacement. And again, this all still equals 1/2 ma v final squared. And this is sort of where we're going to stop for now. This is one equation, and it tells us quite a bit. So let's move on to block B and see where we're at once we do the same thing on block B. So for block B, we have the same idea. Work total should be equal to change in kinetic energy, and I'm going to skip, and that's basically saying it should be equal to 1/2 mass of block B times the final velocity squared, right? The initial kinetic energy of block B was 0 as well. So this is still true, just like the top equation. And so again, let's look down here. And what is our work total on B? We see the tension and the gravitational force are both going to do work, right? Those are both along or against the displacement vector. So none of them are perpendicular, so these will both do work. So that's to say this will just be whatever the work done by gravity is plus the work done by tension, and that should still equal 1/2 mb v final squared. So this is our second step, and now we again just have to solve for each of these works separately, and we're sort of in the place we want to be. So the work done by gravity we see, that is along the displacement vector, so that should be positive. So the work done by gravity will just be force gravity on B times the distance traveled. And then we see here our work done by tension on block B is actually going to be negative, whereas on block A, this work done by tension was positive. Now on block B, the tension actually pulls against the displacement vector, so this will actually be our negative quantity, which is to say minus force tension times the distance traveled. And all of this should be equal to 1/2 mb v final squared. So these are really our two equations. These last two are the two big equations we want to look at. And what we want to decide is does this give us enough information to solve for this v final? And so we can go over and see what we know and what we don't know. So we don't know the tension, right? So that's one unknown we want to start with. The distance traveled, we do know. We're given that is 1.5 meters. The force of kinetic friction, we don't know at the moment, but we can solve directly for that. So if you'll remember from our chapter on friction, the force of kinetic friction is always just equal to mu times normal force. So in this case, that will be mu times normal force on block A. So let's call this force normal as we have over here labeled. So we can break this down right away, and we see the normal force must cancel out our gravitational force on block A. So these must be equal and opposite. So that's to say that the force of kinetic friction on block A must just be mu times mass A times gravity. So this is actually something that we do have. We have mu, we have mass, we have the gravitational magnitude. And so we can plug this directly into force of kinetic friction. So that's actually a known as well. And then our S, again, still known. Mass we know. So really, for this first equation, we have two unknowns, which are the tension force and the velocity. And if we do the same thing on this second equation, we'll see that that's the same scenario here. We don't know the tension, we don't know the velocity, but everything else we do actually know. We know the force of gravity is just mg. So from this, we have two equations and two unknowns. And so if you remember from math, whenever you have two equations and two unknowns, that is a solvable system of equations. So I'll let you guys reference the solution key. But in general in these problems, if you can ever break this down to the point where you get two equations and two unknowns, your problem just becomes some algebra. So please reference that solution key to make sure you can get from here to your answer. But in doing so, you should be able to get that you get a velocity of 2.90 meters per second. And so that's to say that our block B and our block A are going to be traveling with a velocity of 2.9 meters per second after they've fallen a distance of 1.5 meters. Okay, so let's review what we've just done. We first drew our free body diagrams, and then for each block separately, we utilized the work energy theorem to set the total work on that block done equal to the change in the kinetic energy of that block. So this gave us two equations with two unknowns, and then we solved that directly to get our desired velocity. Okay, so I hope you guys found this video helpful, and I hope you sort of have some sense of how to apply the work energy theorem to a concrete scenario. So please leave any comments you have about this video or any of these videos on the links on TED, which should be right next to the video link. Thanks for watching.